Okay, good day. Welcome to the third part of the chapter lecture here in Physics for Future. Okay, in this part, we are going to discuss the energy and power in electric circuits. So, this chapter deals with the formulas and the concepts in the energy, power, and in electric circuits. So, energy and power. So electrical power in a circuit is the rate at which energy is absorbed or produced within a circuit. A source of energy, such as voltage, will produce or deliver power while connected to the load with the connected load absorbs it. So what happens here is if you have a potential difference inside the surface, it produces energy and deliver power while the connected load absorbs it. So we are going to determine the power that the load or the circuit produces. So the power is defined as the potential difference times the current that is being produced. So here we have your V sub AB times the current. So this is the power produced in a circuit or power absorbed in a circuit. So if we have an pure resistance included in our circuit or in a load, then our power input to a pure resistance could be mathematically described as your P is equals to VI is equals to I squared R or V squared over R. So we can also calculate power if we have a resistance R using this formula. So this is the power delivered to a resistor. So you have here the V is the potential difference, I is the current, and R is the resistance. So we have the power output of the source. So what we have here for the power output of the source is that the source as the source producing the power. Okay, the source producing the power. So work is being done rather than by the agent that causes the non-electrostatic force in the upper source. So there is a conversion of electrical energy into non-electrical energy in the upper source at a rate of E times the current, or the potential difference E times the current, or the EMF E times the current. So the power is just, we have EI minus I squared R. Okay, so the power output of the source. So this is the power output of the source. So as you can see here in this formula, the EI is the idea or the theoretical power produced by the source, while your I squared R is the dissipated power produced by the source. So this is now the total power produced by your source. Okay, so it could be VI is equals to EI minus I squared times R. So again, this power is the power that comes from your output of a source. So power output of a source. So this is the power produced by your source. So we have the ideal or the real value of your EMF or your theoretical value of your EMF times the current or the power times or minus the dissipated power due to the internal resistance within your source. Okay? So how about the power input to a source? So power input to a source. So the EI or the electromotive force times the current is the rate at which work is done on the circulating charges by whatever agency causes the non-electrostatic force in the source. The term represents the conversion of non-electrical energy to the electrical energy within the source. So your EI is the the rate of conversion, your EI, your electromotive force times current, is the rate of conversion of non-electrical energy to electrical energy within the source. Then the term I squared is the electrical energy is dissipated within the internal resistance of the source. So mathematically, we can have that one. So this is the total power na. Total power input to a source. So when you say power input to the source, to the source, always remember that to the source, going to the source. So you have this is the total power input to the source. Okay, so we have EI plus I squared R. This is now the total power input to a source. Okay, the total power input to a source. So now let's have an example here. So for the circuit that we analyzed in the previous example, let's find the rate of energy conversion, chemical to electrical, and energy dissipation in the battery. The rate of energy dissipation in the 4 ohm resistor and the battery's net power output. Okay, so let's solve. So let's have first the part A, which is the energy conversion of your chemical to electrical power or electric to chemical energy. So we have A, that is your AI. So that is just your we have your E is 12 volts, 12 volts times your current, which is 2. So we have 24 watts. Times current. So this is the energy converted. This is the converted energy from chemical to electrical energy. Okay, how about the dissipation or the loss energy? The lost energy. So the energy dissipation is we have I squared times R. So your I is now your 2 amperes squared times your resistance or internal resistance, which is 2 ohms. So we have 2 squared, that is 4. Then we have 2 ohms. 2 ohms. So that is 4 times 2, that is 8 watts. Okay, so this is the energy conversion and the dissipated energy of the battery. Now, the rate of dissipation in the 4 ohms resistor. Okay, the 4 ohms resistor. So we are going to calculate using the formula. So we have your VAB times your current. So we have your VAB, which is 8 volts, times your current, which is 2 amperes. Then we have 16 watts. So this is the rate of energy dissipation in the 4 ohm resistor. Well, the battery's net power output is we have power output is equals to I R, which is equal to we have your I, so I squared R. We have your I, which is 2 amperes squared times your resistance, which is 4 ohms. So our answer will be 16 watts. So this is the net power output. Okay, this is the net power output produced by your produced by your source at the 4 ohms resistor. Okay, so this is now your answers. Okay, so I think that's for this session, and this is the energy and power in electric circuit.